All right, so our next section we're going to look at is 18F, where we're going to be talking about symmetry. Symmetry is really important that you understand in mathematics because you can use the idea of symmetry to answer questions without having to do a lot of work if you understand it, particularly when we're talking about graphing and that kind of thing. So, we're going to talk about two different types of symmetry. The first one is we're going to talk about what's called reflection symmetry. Right? And we talked about this a little bit because a reflection simply means a mirror image. So what you have is it's simply reflected in the axis of reflection. Right? So it's an exact opposite on the other side of the axis of reflection. So we've talked about those before. So you see here, they've got the axis of reflection, and that divides that face exactly in half. One side is identical to the other. It's just the distances from the axes are different, right? Okay. So we've talked about those. You've looked at those. The one we haven't talked about is what's called rotational symmetry. Now, we've done rotations. If you're doing a rotation, that means you're just spinning it around the origin, right? But in this case, you're going to be spinning it around the origin in fixed increments. And we'll talk about what that means in just a moment. Okay? So, if it has rotational symmetry, when any point moves to take the place of another point. Okay? So, one point moves to take the place of another. And you're going to see that there's a little bit of mathematics involved here as well. So we're going to expand on that idea so that you can see a little bit more about rotational symmetry. All right? How you can tell that you're dealing with that. Okay. So let's just scroll up. So if you look at diagram 1 there, you'll see that all of the points are going around the origin, and diagram 2 and diagram 3, you'll see that the points are all just moving around the origin. They stay the same distance from the origin. Everything is the same, and that's rotational symmetry. Notice that in the original one, A moved to the place of B, which moved to the place of C, which moved to the place of D, etc. Right? But they all moved in exactly the same position. And that's rotational symmetry. And in this case, they're all moving at 90 degrees. And you can tell that by drawing two perpendicular lines that meet at 90 degrees. This point went to there, this point went to there. So each movement, each time they move, they're moving at 90 degrees. It doesn't always have to be 90 degrees. It could be 45 degrees. It could be 30 degrees. The important part is to remember what happens if something moves all the way around. That's a full rotation. 360 degrees. A full rotation is going to be 360 degrees. So if you're doing these rotations, if they're going to have rotational symmetry, they're going to be divisible by 360. The 360 is going to be divisible by the number they're moving. Okay? And we'll look at a little bit of a formula in just a moment so you can see that. Make sense? Right? It's just a visual thing right now. Don't worry about the math part of it. We'll get into that. Okay? Okay. If you think about, if you're looking at how many degrees they moved, there are two ways you can do this. Okay? You know, first of all, that a full rotation, so do you see things from our past coming back? A full rotation is 360 degrees, right? Okay. Two different cases. Let's just use an A. If you know the angle then you can find the number of movements. So in other words, the number of times you would have to rotate it at that angle to get a complete rotation. So for example, if you want a complete rotation, that's how many degrees? 360 degrees. And if I'm rotating it 90 degrees, then I would simply take 360 divided by 90, which means that it would take 4 rotations of 90 degrees to make a full rotation.
So what's that last word on that?
Movements. This last word? Movements. Just ran out of room. Okay? All right? So if you know the number of degrees, you simply divide by that number of degrees, and that'll tell you how many times you'll have to move it to get a full rotation. Secondly, if you know the number of movements to make a full rotation, then if you divide by that number, you can find the degrees. But every time you're doing this, you're simply going to take 360 divided by something. Either the number of degrees, if that's what you know, or the number of movements, if that's what you know. So you're simply going to divide by what it is you know, and that'll give you the one you don't know. Okay? So say, for example, that I have a shape. Let's picture this. And I want to know how many movements it's going to take to do a full rotation. Well, I know a full rotation is how many degrees?
360.
360. Let's say that I'm moving in 60-degree increments. So take 360 divided by 60, which gives me 6, right? So how many movements would it take to make a full rotation? 6 movements of 60 degrees would make a full rotation. Okay? So whatever you know, divide by that, and it'll tell you the other one. Make sense? So if I know how many movements, I'll divide by that number of movements. If I know the angle then that it's moving, then I'll just divide by that.
What does that number, that letter there say? Like in the circle?
Done here?
No.
Oh, movements. That's the word movements.
Oh.
Okay, so you can always divide. And notice the phrase, the figure has a rotational symmetry of order 4. So the number of, and you need to write that down, guys, the number of movements it would take to make a complete rotation is the order of rotational symmetry. So rotational symmetry, the order of rotational symmetry simply means how many rotations would it make to do a full rotation. And when you've done a full rotation, that means it's right back where it was, so you end up with a new shape that's sitting right on top of your old shape. What does it mean if you do something that puts the other one right back where it started? Do you remember there's a special word for that? It starts with an I. Identity.
I love Mr.
Identity, remember? All right, so you get an identity rotation. Okay? Rotating back to the original position means that it's an identity. Identity always means it's the same thing you started with. Okay? All right. So, let's take a look at a couple of these. See what questions they ask. So in example 13, pull this down. Draw all axes of reflection symmetry for the figure shown opposite, and then write down the order of its rotational symmetry. So, all of the axes of symmetry means anywhere that it would be exactly the same on both sides, right? Well, look at the lines they've drawn. I could cut it right in half. Does that give me two identical parts, two reflections on either side? Yep. I could cut it in half that way, and then the top and the bottom would be a reflection, yes? I could also cut it on this axis, and that means the other two arms would be a reflection of each other. And I could cut it on this axis, and that means that these two arms would be a reflection of each other. Right? So how many different ways could I do that? 1, 2, 3, 4 different lines I drew. Right? Okay. So if you look at your original shape, these pieces, these lines meet at what kind of angle?
90 degrees.
At 90 degrees, right? Each one of these is a 90-degree angle. Therefore, each turn would be 90 degrees because you're only allowed, in rotational symmetry, the top one has to move over to be on top of the next one, and then so forth, right? So they have to move the same amount. So therefore, it has an order, a rotational symmetry order of 360 divided by 90, which is 4. Okay? Now, if you can't tell how many degrees the lines are apart, then you can use your protractor to measure them. They should be to scale, but if they're not to scale, just think about the shapes. You can usually come up with it. Okay? All right. Let's see what's next. So here what they want you to do is they want you to see how many axes of symmetry that letters have, different letters have. Some letters are symmetrical and some aren't. And some are symmetrical in more than one spot. So let's just look at a couple. If you have the letter A, does the letter A have any axes of symmetry?
Yes, sir.
Where? Straight down the middle, and then both sides are identical. Anywhere else?
No.
No. So that's the only one for the letter A. How about if I chose the letter H? Does that have any axes of symmetry? Yeah, I can go straight down the middle. Oops, that's not quite straight down the middle, but you get the idea. And I can go straight across as long as I'm going across that bar in the middle of the H. Anything else? Yeah. As long as I'm hitting the top and the bottom, I can go along that way too. Anything else? Nope. Those are the axes of symmetry. Yeah? Which tells you that each one of those is how many degrees? 45 degrees. So therefore it would take me, it has rotational symmetry as well. How many times would it take for me to rotate it around and get back? 8 times. So rotational symmetry order 8. Good job. All right. Let's look at another one. Capital B. Where? Yeah. Horizontally through the middle, right? Okay. Not vertically, but horizontally through the middle. Anything? Shh. Anything else? Is there a diagonal here? No. So that means that line is going through at how many degrees? 180. So the rotational symmetry, the order of rotational symmetry would be 2. Pretty easy? Shh. All right. O is a tough nut. Why? It's completely symmetrical everywhere. Yeah. So we won't be doing O. How about P? Doesn't have any. Yeah. Okay. So you can have shapes that have no symmetry, right? Okay. Don't want to do A. X is no big deal. Just remember it's got symmetry across here. Across there. Horizontally. Diagonally. Right? Okay? Why? Down the middle. Anything else? That's it. Okay? All right. Let's see what else they do. Now they're going to give you some shapes, and you're going to just do the same thing. Find any axes of symmetry, and then tell the order of rotational symmetry. Right? Again, just find the axes, and then that will tell you how many degrees it's divided up into, and then you'll move them around, and then you'll count them up and divide 360. Okay? So. All right. And that's that lesson, so we'll be working on those.